Okay, for problem 1.4, lump thermal model for thermocouple, we wish to estimate the dynamics of a cold thermocouple prop suddenly placed in a hot flowing fluid stream for the purpose of temperature measurement. The prop consists of two dissimilar metal wires joined by soldering at the tip, and the wires are then encased in a metal sheath, and the tip is finally coated with a bead of plastic to protect it from corrosion. Take the mass of the soldered tip plus plastic bead to be M, okay, and with specific heat Cp. Denote the heat transfer coefficient as H. A. If the effects of the thermal conductivity can be ignored, show that the temperature response of the prop is described by the following equation, where A denotes the exposed area of the prop tip and T, as a function of T, is its temperature. B. The lump the explicit parameters to form the system time constant, and for constant Tf, define a new variable theta, Tf minus T, and show that the compact form results. Equation 2, where the system time constant is defined as the one in equation 3. C. Integrate the expression in B using the initial condition T at O equals to TO, and show that the fourth equation, and equation number 4. And D. Rearrange the expression in part C to obtain equation number 5, and thus show the temperature excess is 63% of the final steady state value after a time equivalent to one time constant has elapsed. This also represents a quick and easy way to deduce system time constants based on elementary experiments. Okay. So this is your thermocouple suddenly dipped in the water. All right. Now we look here. Okay, so A denotes the area of the prop tip, and T as a function of T is its temperature. So we can define that Q, capital Q, is heat accumulated in the prop. And QC is the heat from convection. Right? By performing simple energy balance, we get QC to be dq over dt. Therefore, HA Tf minus T equals to mCp dt over dt. Okay, so for part B, lump the explicit parameters. To form the system time constant, and for constant Tf, define a new variable and show that the compact form results in equation 2. Okay, so from this part here, okay, I'll write down this one is B. mCp dt equals to HA Tf minus T. Okay, so we bring HA over, equals to Tf minus T. Okay, so we take this, we lump these variables as tau, okay, which we get this. Okay, then we let theta to be equal to Tf minus T. Okay, and d, if we differentiate this, dt to d theta to d theta, d theta to dt equals to -1. Okay, therefore d theta over dt is equal to d theta over dt multiplied by dt over multi, which gives us negative dt over dt. Okay, this one is this, right? Meaning to say, we therefore, okay, so this one we can replace with this. We get tau multiplied by negative d theta over dt equals to theta, because this one is theta. And we take out the negative constant, so we get tau d theta over dt equals to negative theta. Very simple. Okay. So part C, integrate the expression in B using the initial condition T at O equals to T on show the equation. So from B we know that tau d theta over dt equals to negative theta. Okay, so we get this form when we rearrange. Okay. Now integrating this, we get theta equals to c exp negative t over tau. Okay, and theta we have defined previously is tf minus t equals to c exponential of negative. So at t equals to 0, t equals to to. Okay, so tf minus to equals to c exponential, this one is 0, which is 1, equals to c, right? Therefore, we can finalize it as tf minus t equals to c, this one is c tf minus to exponential of negative t over to over tau. Okay, move this over, rearrange. Okay, then we move, we multiply it. We multiply by -1, So we get T minus TF over TO minus TF equals to oops, tau. Okay. So for part D, we arrange the expression in part C and to obtain the following equation and thus show that the temperature excess is 63%. Yeah. Right. So write this down. So for part D, so we have T O minus TF over T O minus TF minus T minus TF over TO minus TF equals to okay. So we lump everything together. So we know that this is 1, right? Okay. Divided by TO minus TF equals to 1 minus exponent negative T over tau. Okay. And that leaves us with TO minus TO minus TF so when T is equals to tau, right, then this one becomes 1. Okay, yeah, negative 1. Okay, so we get 0.63, which is 63%. Okay, now for part 4, oops. Problem 1.5, distributed thermal model for thermocouple. Okay. If the plastic bead covering the tip of the thermocouple is described in problem 1.4 is quite large, okay, then since plastic usually sustain a very low value of thermal conductivity, then the simple lump model solution becomes quite inaccurate. To improve the model, we need to account for the thermal conductivity in the assumed spherical shape of the plastic bead. Assuming that the bead is in perfect shape, perfect sphere, contacted everywhere by external fluid of temperature T, perform a shell balance on an element of volume 4 pi r squared delta r and show that equation 6. Okay. And B. Perform an elemental heat balance at the surface of the sphere and deduce equation 7, where r is the radius of the plastic sphere. Okay, we look at part A. So because it is quite large, therefore we have to do shell balance as such. Okay, because it is quite large. What is it? Right up. Okay. Now, the rate of heat in by conduction at R is 4 pi r squared q r at R. Okay, and the rate of heat in by conduction at R plus delta R is 4 pi r squared q r plus delta r. Okay, so if we do the balance, we can write 4 pi r squared q r at R minus 4 pi r squared q r at R plus delta R equals to dq dt. Okay, now q is mcp t minus t reference, right? Therefore, m is 4 pi r squared delta r rho cp. Okay, t minus t ref. Okay, we can then substitute this one back in. Becomes 4 pi r squared q r at R equals to, okay, that is dq per dt. So 4 pi r squared delta r rho cp dt per dt. Okay, so then we will divide everything by 4 pi delta r, and we take delta r as limit approaches 0. We get negative negative, oops, sorry, as delta r approaches 0, we get r squared qr at R plus delta r. Okay, because we have multiplied with negative, so this one bring is brought in front over delta R equals to R square rho Cp dou T dou small t. Okay. Therefore, from here we get the limit gives us equals to R square rho Cp dou T. Okay, so we substitute QR equals to negative K dt dr. We should get okay. So the negative and the negative here is cancelled off. Okay. We rearrange the equation. We should get this. R squared. Okay, R has to keep inside because it is a function of R. Okay. Now for part B, we perform an elemental heat balance at the surface of the sphere and deduce that negative K dt over dr is equal to H multiplied by T minus Tf at R equals to R. At R equals to capital R. Okay. B at R equals to R, where R is the radius of the plastic sphere. Therefore, we can do a simple heat balance where Q, the heat conductive heat, is equal to the convection heat. Therefore, negative K conductive heat is given by this negative K over dt dr at R equals to convective heat is H Tr minus Tf. Okay, so that's all for tutorial 5.